Hello everyone, and thanks for watching Edupedia World videos. In this video we'll start a new unit called Electromagnetic Induction. Now up till now we first studied electrostatics, then electrodynamics, then magnetostatics. Electricity and magnetism were up till now seen as two separate entities, and that was the way it historically came about. But actually electricity and magnetism are part of the same thing, which we now call electromagnetism. So before that, the reason they were considered two different things is because they dealt with different sort of objects. Electricity had to do with what happens when you rub a piece of glass rod with silk, or when you run a comb through your hair and then it's able to attract pieces of paper. Right, and that's a temporary phenomenon. A glass rod does not attract silk, it only attracts silk if first you rub them together so that electrons are transferred from one body to another. Then there were other objects like iron and compass needles, which always pointed towards a particular direction and which behaved more like magnets than electricity. So therefore we started dealing with two different topics, electricity and magnetism. But in the 18th century, Benjamin Franklin and many other people did many experiments which started to prove that electricity and magnetism were actually related. And one of those experiments was done by Faraday, and that was something like this. He just made a loop with a galvanometer. If you don't remember, a galvanometer is something which has a needle and the needle deflects if a current is passing through the loop. And this had a big circular loop attached to it. Right. So there's no current flowing because there's no battery here to provide an EMF. We just have a loop like this. Right. Now what he did was he took a magnet, a bar magnet, let's say, with a north and south pole, and he moved it towards and away from this loop. And he saw that whenever the bar magnet was stationary, there was no deflection in the galvanometer, but whenever the bar magnet was moving, the galvanometer needle deflected. When the bar magnet was moving towards the loop, the needle pointed in one way, and the bar magnet was moving away from the loop, it pointed in another way. However, the important thing was that simply the presence of the bar magnet did not ensure that the galvanometer needle got deflected. The bar magnet had to move. There were a number of other experiments also done by many people, and this experiment, among others, conclusively proved that electricity and magnetism are related, because the galvanometer moving is purely an electrical phenomenon. The galvanometer needle deflects when there is an electric current flowing through the loop, and this bar magnet only produces a magnetic field. So we see here that a magnetic field and an electric field for the first time are actually related. And Faraday did a number of experiments, and finally he formulated what he named as Faraday's law of electromagnetic induction. Now I'll just write the whole law first. It says that whenever the flux we've seen the term flux before. When we were talking about Gauss law, we saw the electric flux, which was the flux due to the electric field. Right. So whenever the flux of magnetic field now through an area bounded by a closed loop, whenever the flux of magnetic field through an area bounded by a closed loop changes, an EMF is introduced in the loop. Now this is the qualitative form of Faraday's law, which basically says that if you have a loop, let's say a loop of current carrying wire, and there is some magnetic field present in the universe, then obviously this current carrying two-dimensional loop, not current carrying but potentially current carrying two-dimensional loop, will have some magnetic flux through it, right? Because there will be magnetic field lines passing through it. If the magnetic flux changes, in that case an EMF will be introduced in the loop, and of course if this is a current carrying loop, then there will be a current flowing, which will be found by Ohm's law, EMF divided by the resistance. Now this is a qualitative form, but he also gave it quite quantitatively. And what he said was that the EMF, induced EMF, is given by minus d phi by dt, where phi is the magnetic flux, and if you know the formula for electric flux, magnetic flux comes quite naturally enough. It is the integral of B dot ds. ds is a small area vector, you integrate it, you get the total area. So integral of B dot ds is the total flux flowing through a loop. Right. Now notice there's a minus sign here. We'll come to that in a second. Before that, let's just do something which comes quite naturally. If the resistance of the loop is R, let's say this is the loop and the total resistance of the loop is R, then the current flowing through the loop will be minus 1 by R d phi by dt by Ohm's law. Right. So this is one of the most important things, that whenever it changes, if simply a magnetic field is present near a current carrying loop, that does not ensure that there will be a current in the loop. The magnetic flux through that loop has to change. Now when we had our original loop in Faraday's experiment, like this was the galvanometer, and here there was another loop. If we just kept the bar magnet here, it would have some magnetic field, and that would create some magnetic flux through the loop, and that's it, nothing would change. But when we start moving the bar magnet, the magnetic flux through this loop changes, and when the magnetic flux through this loop changes, there will be an there will be an EMF induced in the loop. And if this loop has the ability to carry current, if it has not an infinite resistance, another way of saying it would be, then there will be a current induced in the loop. Now the current is given by another law, which is called Lenz's law, and it's simple enough. It basically says that the direction of induced current or induced EMF, it's the same thing. The direction of induced current is such that it opposes the change that has induced it. And that's where that minus comes from. We saw that minus in another place when we saw the force of a spring by Hooke's law. F was equal to minus kx, because it was always opposite to the displacement. The direction of induced current is such that it opposes the change. That is why I is equal to minus 1 by R d phi by dt, and E is equal to minus d phi by dt, where phi is equal to integral of B dot ds. Right. What does that mean? So let's say there's a magnetic field going inside the plane and I have a loop, right? It does not carry any current. Now if the magnetic field starts increasing, that means the flux in this loop inside the plane will start increasing. So the current will be such that the flux inside the loop should decrease. That means the flux outside, sorry, I'm saying inside the loop, it should be inside the plane. I'll repeat it. This magnetic field crosses depict that the magnetic field is going inside the plane, away from the viewer. If we have a loop and the magnetic field increases, that means the magnetic flux increases. So the current will be in such a direction that it would like to bring the magnetic flux to its original value. So the current will be in this direction, coming out of the plane. Now that's not really a direction of the current. If this is the direction, then by right hand thumb rule, this will be the direction of the current. Right. However, if this is the magnetic field and the magnetic field was decreasing, that means the magnetic flux due to the field going away from the viewer is decreasing. So the induced current would want to bring the flux to its original value. So it would induce a current such that that would add to the original magnetic field. In that case, the current would have this sense as well, that is this one. And you can see if the current is in this direction, then by right hand thumb rule, the magnetic field due to this induced current will be in this direction. So it will try to bring the flux back to its original value. Now let's see some different examples in which how this law is formulated. The first and most straightforward example would be this, and we know whenever we deal with magnetic field, the analog of a single charge is an infinitely long current carrying wire, which is the most fundamental quantity. So this is an infinitely long current carrying wire carrying a current I, and let's say we have a loop over here. Just a simple circular copper ring, no EMF, no batteries, nothing is attached. Now because of this current, there will be a magnetic field in this direction. Right, when you take your right hand and thumb points towards the current, then this will be the direction of magnetic field. So the direction of magnetic field here will be going inside the plane. Right, on this side will be coming out of the plane, on just behind this will be towards the left, in front of this will be towards the right. Anyway, it will go like this. If your eye is up here, then it will look to be going in the anti-clockwise direction. Right. So let's say what will happen if this current starts increasing. If this current starts increasing, this magnetic field starts increasing. Right. Magnetic field is proportional to the current for an infinitely long wire, mu naught I by 2 pi r. So if the magnetic field increases, this area is obviously constant, then the magnetic flux through this loop starts increasing. Right. So the current induced in this loop will be such that that current will have a magnetic flux in the opposite direction. So let's just start from the basics and take both the cases. Let's say if it was going in this direction, and let's say if it was going in this direction. If the current was flowing in this direction, then the magnetic field due to this current, by the way, this current will now be called the induced current because it is induced by this change in magnetic field, and the magnetic field due to the induced current is called the induced magnetic field. So this will have an induced magnetic field which will go inside the plane, and this will have an induced magnetic field which will come out of the plane. Right. So if the magnetic field inside the plane is increasing, then the current will be such that it wants to decrease the magnetic field in that direction. So this will be the answer. It will be in the opposite direction. However, if this current starts decreasing, then the magnetic flux going away from the viewer into the plane will start decreasing. So the induced current will be in such a way that it will add to that flux to bring it back to its original value. How will it add to the flux going away from the plane? The current will be in this direction, so that some flux will be added. Right. So this is the first simple case. Another case could be if you have a magnetic field. I won't draw it everywhere. Let's say it's all throughout the plane. Right. You have a magnetic field everywhere going inside the plane, and you have a systematic arrangement like this, but the magnetic field is going inside the plane everywhere here, right? So if this is an arrangement you have, and you take this particular rod or this particular wire and you start moving it towards the right, in that case, now if you have flux that is integral B dot ds, there are three ways to change the flux. You could change the magnetic field, which is what we did in the previous example, or you could change the area, or you could change the angle between them. How do you change the area? Simple, you just take this towards the right. Now this is not a loop because these are just two ends, right? They're not connected to anything. So if you look at this loop, right, this loop has the same magnetic field going through it, but its area is increasing. That means the flux through it is increasing, so the current will be such that the flux through this loop should decrease. So the current will be in the opposite direction, right? So if you take this, then this is the magnetic field, or this is the direction of the magnetic field, and it is increasing. So the current will be in the opposite direction, and the current will be like this, right? Now, so we've seen these two examples. In one, we changed B, kept the area the same. In the other, we changed the area and kept the magnetic field the same. But we could also keep both of them the same, and the angle between them could change. How would you go about solving that question? Again, let's just assume that there's a magnetic field present everywhere inside the plane, and you have a square loop. Now, initially, there will be some magnetic flux through this loop. Now what would happen if this loop, instead of being placed like this, was rotated by 90 degrees about this axis? Right. Now this loop would be like this, and now there would not be any flux flowing through it, right? Because the area vector will be in this direction, the magnetic field will be inside the plane, they'll be perpendicular to each other, B dot ds will be 0. right? So now there will not be any flux flowing through it. So all you need to do is take this loop and rotate it about an axis like this. You could rotate it in many ways. You could rotate it about an axis like this if you wanted to, at an angular speed omega. And if this loop is rotating about any one of the two axes, then the magnetic field is constant, the area of the loop is constant, but the angle between them is changing. So the magnetic flux through this loop will change. And what will be the direction of induced electric field? Again, it will be opposite to that, such that the magnetic flux is brought back to its original value. And it will depend on in what sense is this loop being rotated. Right. So this sort of tells us the relationship between electricity and magnetism. A changing magnetic field induces an electric field. I'll just write it now. A change in magnetic field produces an EMF and hence an electric field. These are the two symbols. I hope you're familiar with them now. This is for the EMF and this capital E is for the electric field. Right. Now we've discussed how this field works, how this electromagnetic induction works, but where does this come from? In other words, what is the origin of this induced EMF? So let's look at that right now. So there are two ways in which this EMF can be induced. The first of them is when we change the area of the loop, or when we move basically a current carrying wire in a constant magnetic field. In that case, the EMF induced is called motional EMF. Right, because it is induced due to the motion of the current in some way or another, due to the motion of the current carrying loop in some way or another. So let's just take the simplest example. We have a magnetic field everywhere pointing inside the plane, and we take a standard rod, not a current carrying rod but a potentially current carrying rod. That is a rod that does not have resistance infinite. If it doesn't have resistance infinite, then it can technically carry at least some current, right? The length of the rod is L and we move it with a speed v towards the right. What will happen? Every electron in this rod will experience a force due to this magnetic field. Now this comes from the initial formula which we learned in the beginning, Lorentz force law, and every electron will experience a force of E times VB. Right, minus EVB actually, if you want to be careful about the sign, but right now we're just talking about the magnitude. So EVB, why? Because it was Q times V cross B. Now V is in the right direction, B is away from the viewer, so V cross B will be in the upward direction. Right. Now what that means is every electron will experience a force in the downward direction, and that is equivalent to protons facing a force in the upward direction. That does not actually happen because protons are stationary and electrons are the ones that are moving. But since we take the positive current to be the opposite of the direction of electron flow, which we assume to be the direction of flow of positive charges, so the force on electrons will be downwards. That means there will be a current that will be upwards in the wire. Right, not actually a current, but there will be some motion of electrons, some motion of current upwards in the wire. Now what will happen is the electrons will move down here, so they'll create a negative charge. The protons will, or the deficit of electrons will create a positive charge on the upper side, so there will be an EMF induced in this direction. Right, now what will happen is this this positive charge and this negative charge will start creating its own electric field, right? And that electric field will be in this direction. So the original force on the positive charges in the upward direction, finally force of the positive charges due to these induced charges in the downward direction, and eventually they will cancel each other out. This is the same principle which you've seen in conductors. When you have a conductor and there's an electric field outside, that electric field will cause positive charges here and negative charges here. Those charges in turn will have an electric field in this direction, and since there are an infinite number of charges available in a conductor, you will eventually have enough charges so that this electric field balances this electric field, and the net electric field inside is zero, and there is no more charge accumulation. That is the same thing that happens here. All positive charges experience an upwards force, they go upwards. This positive and negative charge end up creating a force downwards, and in the end those forces balance out. So what is the electric field in this direction? Let's say it's E in the downward direction. right? So now a single positive charge here, let's say a charge Q, experiences a force of QVB upwards due to the motion of this rod, and experiences a force QE downwards, right? And when these two balance each other out, then VB is equal to E, right? So we have found out the value magnitude of the electric field, induced electric field in this rod due to the accumulation of the charges. Now if there is an electric field induced, that means obviously there will be a potential difference. The potential difference in this direction will be E into L, right? And this length is total L, so the EMF or the potential difference will be VBL, positive to negative. So this is the EMF. Now this is not a loop, this is just a single wire or a rod, right? The EMF in a single straight wire of length L in a constant magnetic field B when it moves with the speed V is VBL. Now the speed V has to be perpendicular to the magnetic field, otherwise V cross B will be 0, right? So the EMF induced in this rod or this wire is equal to VBL. We could have actually found this another way. By the way, this EMF is called motional EMF, right? So motional EMF is EMF that is produced due to the motion of parts of a circular loop or parts of any loop, right? When I say circular loop, I tend to use circular loop because that's what we see in magnetism, but I should technically be saying any current carrying loop. So if there's an any current carrying loop and any part of the loop moves, then the area of the loop might change, and the EMF induced because of that is called motional EMF. Let's see this VBL formula in another way, a way which you already seen before. So again, let's assume that there's a constant magnetic field inside the plane, and this is an example which you've seen before. Let's assume that the constant magnetic field is only till here, right? So there's no magnetic field here, and these are all potentially current carrying wires, and this wire is going with the speed V, right? And everywhere here there is a magnetic field. So now this long wire, this long wire, and this wire, all three of them are stationary, so they will not have any motional EMF developed. But this wire will have a motional EMF developed, and the way I generally see it is simply V cross B is the direction of the movement of charge. So V in this direction, V cross B is upwards, so positive charges will be here, negative charges will be here. That means now this loop will be equivalent to a loop which has a battery over here of EMF E is equal to VBL, right? So this we calculated VBL by using motional EMF, but what if we directly used Faraday's law of electromagnetic induction? So if this length is L, then this length is also L. Let's say this length is B and this length is B, right? So in that case, the magnetic flux will be, so the magnetic field is B. Let's take this to be something else. Let's take this to be Lm, just for the sake of it. Magnetic field is B, right? So the flux will be B times the area. What is the area? Lm. So what is the rate of change of flux? d phi by dt. That will be d of this by dt. Now B is not changing, L is not changing, but M is changing. As this rod moves towards the right, this length is increasing. So M is increasing, and dm by dt, which is the rate of increase of M, is V, right? So this will be dm by dt, and from that what we get is EMF is equal to BLV or VBL. Now the direction will be, since the flux in this direction is increasing, the current in this loop would be such that the flux is in this direction, which means this would be the direction of electric current or the direction of EMF. Now actually the EMF is not spread throughout the whole loop. We got the same answer here, but from the previous case we saw that these three rods actually have no EMF developed in them, and the only EMF developed is in this rod because it's the one moving. So we could again replace this rod by a simple battery, and the battery would have an EMF E is equal to BLV. If you wanted to calculate the current, that's easy enough, the total EMF divided by the resistance. However, in this special case you'll have to be careful, because if you take the resistance is also changing with time, because as the area of this loop increases, this length and this length will keep on increasing, and they will contribute greater and greater resistances. So that's one thing which might make this problem slightly complicated. So we've seen what happens when actually the loop itself is changing in some way to create an induced EMF, and that EMF is called motional EMF. What if the loop is stationary and the magnetic field is changing? In that case, the induced EMF is created due to what is called the induced electric field. Now the first question we would need to answer before talking about this is, how is it that the changing magnetic field can produce an electric current? We know that magnetic fields are always proportional to the velocities, and so magnetic forces never do any work. If electrons are stationary, then no matter how much magnetic field you change, the electrons will not experience any force because Q V cross B will be 0. So how does the EMF start changing? How is there a force on the electrons? Well, the answer to that is the induced electric field. We know that the magnetic field can never do any work, yet we know that when the magnetic field changes, the electrons start moving. So the only possible explanation within our realm of understanding of electromagnetism would be that a magnetic field changing magnetic field implies an induced electric field. So whenever a magnetic field in a region changes, there is an induced electric field in that region, and it is the induced electric field and not actually the magnetic field that causes the electrons to move, because electric fields can do work, but magnetic fields can never do any work. Now this induced electric field is non-electrostatic in nature. It is also non-conservative in nature. And that means we cannot define a potential corresponding to this field. So that it's harder, but it's sort of easier in a way for us because we don't need to bother with the potentials. It is also created due to changing magnetic fields, not due to charges. So therefore induced electric field lines are always loops, just like magnetic field lines. They do not have any starting or ending points. Right? They are created simply because the magnetic field in a region is changing. Now, a changing magnetic field will always create an induced electric field. But for a current to be there have to be some electrons, right? If I have an electric field in vacuum, there is no current. So, a changing magnetic field will always cause induced electric field. However, the presence of a current carrying loop is necessary for a current to be carried. There have to be electrons to experience the force due to, so this should be U. There have to be electrons which experience the force due to the induced electric field. So only then will there be an actual current. If there are no electrons, there will be no current. Right? So what have we seen up till now? The first thing we've seen is there is an induced EMF which is equal to minus d by dt of integral B dot ds. Whenever the magnetic flux through a loop changes, there is an induced EMF. If the area of the loop is changing or the parts of the loop are moving in some way, then the EMF developed is due to motional EMF, which is simply because of the Lorentz force law. And when the magnetic field is changing but the loop is stationary, in that case the changing magnetic field produces an induced electric field which is non-electrostatic in nature, which does not have any starting or ending points, and that electric field is ultimately responsible for the induced EMF. That's it for this lecture. We'll introduce new concepts related to electromagnetic induction like self-inductance and inductors in the next video. Thank you.